Okay, so as blood moves to the heart, one of the major things we can measure is called the mean arterial pressure. This is the actual blood pressure within the aorta during one cardiac cycle. That's one systole and one diastole. We abbreviate mean arterial pressure as MAP. And the MAP has a formula with a couple of different variables that determine what that pressure will actually be. The first variable is your cardiac output, which is shortened to CO. And that's the amount of blood that we have pumped in 1 minute. And cardiac output depends on two variables. It depends on stroke volume, it depends on heart rate. So stroke volume is the amount or the quantity of blood pumped in one single heartbeat. And then heart rate is just the number of heartbeats per 1 minute. So when we multiply the heart rate by the stroke volume, we'll get the cardiac output, which is the first portion for figuring out the mean arterial pressure. The second component is a little more simple. That's just the peripheral resistance, which we shorten to PR. And peripheral resistance is just the resistance acting against the unidirectional flow of blood. So all veins and arteries have some level of resistance within them. And whatever that resistance may be, we can factor that in along with the cardiac output. When we multiply these together, they determine the MAP. So we have a directly proportional relationship. If we increase cardiac output, we increase mean arterial pressure. If we increase peripheral resistance, we increase mean arterial pressure, and vice versa. If either of these drop, then mean arterial pressure drops. There's a handful of factors that also affect mean arterial pressure. And the big ones are pH, blood pressure, and oxygen levels, along with CO2 levels. So for your cardiac output factors, that's the CO. If we manipulate the blood pressure, the pH, or the oxygen levels, and we lower those will lead to increased mean arterial pressure. Or if we increase the CO2 levels, that will also lead to increased mean arterial pressure. Additionally, any sort of physical stress in the body with exercise, or any sort of emotional stress in the body with intense emotions like grief or anxiety, that can potentially increase cardiac output as well, which will ultimately increase mean arterial pressure. For peripheral resistance, which also can lead to, if we increase that, to increases in mean arterial pressure. Again, if we decrease blood pressure, pH, or oxygen levels, that will lead to an increase in mean arterial pressure. Also, if we increase our CO2 levels, that will lead to an increase in mean arterial pressure. So like I mentioned, there is a directly proportional relationship with cardiac output and mean arterial pressure, and peripheral resistance and mean arterial pressure. So if we change one, the mean arterial pressure is going to go up, or if we decrease the other, or if we decrease one of the variables, then mean arterial pressure will go down. So within the heart, we have a couple of different ways that we can regulate. We have intrinsic regulation and we have extrinsic regulation. Intrinsic just means within the heart itself. So the heart has a couple of different qualities that allow it to change how it's reacting. The first quality is called preload, and this is the amount of stretch that we have on the ventricular walls, the actual ventricles, the two chambers that are pumping the blood. So if we have a greater preload or a greater amount of stretch, there has to be a greater amount of force exerted to push that blood out of the ventricles. Ultimately, that's going to lead to a greater cardiac output because we have a greater stroke volume. The other quality for intrinsic regulation is called afterload. And this is the pressure of just the left ventricle that we need to move blood against the resistance of the aorta into the aorta. So extrinsically, we have a lot more mechanisms that we can utilize to regulate the heart. And extrinsic just means outside the heart. So we're talking about neurological control or hormonal control. So with our sympathetic nervous system, we can have stimulation along that neural pathway through cardiac nerves. By stimulating those cardiac nerves, we can increase the heart rate, which in turn increases cardiac output. and ultimately increases contraction force. Additionally, we can utilize the parasympathetic pathway through what's called the vagus nerve. And the vagus nerve within the brain can be regulated to decrease heart rate through the neurotransmitter acetylcholine. This will hyperpolarize the heart, which basically means that it won't be able to have an action potential and fire action potentials as rapidly, so the heart won't be contracting as quickly or with as much of a steady rate. Then we have hormonal control with the hormones epinephrine and norepinephrine that are released from the adrenal medulla within the kidney. So these will occur in response to any sort of physical activity, if we're exercising, or if there's any sort of intense emotions or stresses, those can release those hormones as well. And in order to regulate itself with all of these intrinsic and extrinsic conditions, the heart has a couple different receptors within it to monitor the environment and maintain homeostasis. So the two big receptors you need to be aware of are your baroreceptors and your chemoreceptors. Your baroreceptors are responsible for detecting changes in blood pressure. Ultimately, if there is a change that's too high or too low within the heart, there will be a signal to the brain that we need to either increase or decrease the heart rate. And then for your chemoreceptors, those are about detecting changes in pH, changes in carbon dioxide, and changes in oxygen levels. So depending on if pH, carbon dioxide, or oxygen gets too low, these can sense those deviations from the normal range and then act accordingly, whether it's increasing heart rate or decreasing heart rate to accommodate for them. So to go through a feedback loop with a baroreceptor reflex, baroreceptor reflex detects blood pressure. So right here that I'm circling, we have our normal range that we like to stay in for blood pressure ranges. And going with the loop up above, if we have blood pressure increase too far outside that range, those baroreceptors pick up on it. Baroreceptors are located within the carotid arteries within the heart. That will then signal the brain that we need to have sympathetic stimulation and some parasympathetic stimulation to then change the heart rate itself. Those stimulatory pathways will then go to the synatrial node and ultimately fire less action potentials, thus decreasing the heart rate as well as the stroke volume, ultimately lowering blood pressure. On the other hand, if we have blood pressure deviate too low, now the homeostasis is disturbed and that we have the blood pressure needs to be brought back up. So those baroreceptors within the heart pick up on that change, signal the brain that there needs to be stimulation from the sympathetic and parasympathetic pathways, which will then stimulate the synatrial node, which conducts those action potentials in the heart, to then fire more action potentials to speed up heart rate and ultimately increase stroke volume, which will in turn increase blood pressure, getting us back into that normal range. Then an example with the chemoreceptor. So the chemoreceptor regulates pH, oxygen levels, and carbon dioxide levels. But in this example, we're just looking at pH. So first example, first section of the loop we have is when blood pH increases too much, so the environment is getting a little too basic. The chemoreceptors within the brain are going to detect that increase in blood pH, usually because we have too low of CO2 levels within the blood, and it is ultimately going to stimulate the heart and the adrenal medulla. So for the heart stimulation, it's going to basically tell the synatrial node that we need to decrease the action potentials fired, which is going to decrease the heart rate and stroke volume overall, ultimately leading to a decrease in blood pH levels. Then if we have the pH get too low, gets too acidic, the drop in pH will be detected by the brain within the chemoreceptors. That will then send stimulation to the heart, to the synatrial node, in order for the heart rate to be increased because we're firing now more action potentials, which will increase the stroke volume and increase blood flow to the lungs, thus increasing pH back into our healthy normal range. Additionally, in terms of stimulation from the hormonal level, if pH gets too high or too low, we can use hormones released from the adrenal medulla, like your epinephrine and your norepinephrine, to ultimately increase or decrease heart rate to adjust for changes in pH as well. And that'll do it for chapter 20. Next is chapter 21.